Somewhere in the vastness of the cosmos, there exists a place where light falters, and matter seems to vanish. An immense region of space so empty it defies comprehension. This is the Great Void, a colossal stretch of nothingness that challenges our understanding of the universe itself. Far from being just a blank space, the void is a cosmic enigma, a vast expanse where the rules of physics appear to unravel. In a universe filled with stars, galaxies, and swirling nebulae, how can a place so empty, so profoundly silent, even exist? The discovery of these voids, regions of the universe where galaxies are conspicuously absent, has transformed our understanding of the cosmos. In the dark heart of space, these voids stretch over hundreds of millions of light years, growing ever larger as the universe expands. They are not mere gaps in our observations, but active, dynamic features of the cosmos, shaped by forces we are only beginning to understand. As the universe races outward, the Great Void continues to expand, consuming everything in its path. But what exactly are these voids? Why do they exist? How do they relate to the forces that drive the universe's expansion? And, most profoundly, what does their existence tell us about the true nature of time, space, and the universe itself? This journey takes us deep into the heart of one of the greatest mysteries of modern science. From the earliest discoveries of cosmic voids to the speculative theories that now shape our understanding, we explore the Great Void, not as a simple absence, but as a place of infinite possibility, where the fabric of the cosmos itself seems to stretch beyond the limits of our comprehension. Discovery phase. In the early years of the 20th century, the very nature of time, that most fundamental measure of existence, began to unravel. The world, for all its precision and regularity, suddenly found itself confronting an uncomfortable truth. Time, as we had known it, was not the absolute, unyielding force we had believed. Instead, it was a fluid, malleable construct, shaped by the very fabric of the cosmos. The revelation came in 1905, when Albert Einstein, in the quiet of his patent office, penned what would become one of the most profound discoveries in the history of science. Time, he proposed, was not a constant. It was relative. The flow of time itself could stretch or contract depending on the observer's position and motion. His theory of special relativity shattered the long-held notion that time was the same for everyone, everywhere. It was not an immutable measure, ticking away at the same rate for all. Instead, it was bound to the speed of light, the one constant in the universe. But this was only the beginning. Einstein's imagination would soon take him deeper, to the very core of the universe itself. In 1915, he revealed his theory of general relativity, a revolutionary leap forward. Time, he explained, was not just relative, it was intricately woven into the very fabric of space. Together, they formed a single entity, spacetime. This fabric, like a vast sheet stretched taut, could warp and bend under the influence of mass and energy. Planets and stars with their immense weight would cause ripples in this fabric, distorting the flow of time itself. What we once believed to be a fixed, absolute progression of moments was, in fact, something far more flexible. A river whose course could be shaped by the presence of cosmic objects. The implications of this discovery were profound, but they would take decades to be fully understood. In 1919, the first confirmation arrived, an experiment led by the British astronomer Arthur Eddington during a total solar eclipse. As the moon passed between the Earth and the Sun, Eddington observed something extraordinary. The starlight, as it passed near the Sun, bent, Einstein's theory had predicted this bending of light due to the sun's mass-warping spacetime. The starlight, like a river, was diverted by the gravitational pull of the star, confirming that time and space were not mere abstractions, but a real, tangible structure of the universe itself. For years, these ideas existed more in the realm of theory and mathematical elegance than in tangible evidence. But then, in 1967, a discovery came that would confirm the malleability of time in an entirely new way. In the sterile, cold halls of a radio telescope in Cambridge, England, a young astronomer named Jocelyn Bell Burnell was scanning the skies when she stumbled upon an unusual signal. It was a regular, rhythmic pulse, a cosmic heartbeat coming from deep within space. It was unlike anything ever observed before. A pulsar, the remnant of a massive star that had exploded in a supernova and collapsed into a rapidly spinning neutron star. These cosmic clocks, emitting regular pulses of radiation, kept perfect time, down to the millisecond. In their constant, unyielding precision, they provided the first evidence that time itself could be measured across the vast distances of space, unaffected by the distortions of gravity, a true cosmic reference. The pulsars became one of the most crucial tools for testing the theory of relativity. Their precision revealed that time could be bent in ways unimaginable, shaped by the gravitational forces of massive bodies. In fact, the pulsars themselves could reveal the curvature of space-time, an idea that had once been mere speculation. As the years went on, this newfound understanding of time would continue to evolve, deepening our appreciation for the strange ways in which the universe operated. The more scientists looked, the more evidence they found that time was indeed not constant, but rather shaped by the universe itself. Perhaps the most striking example came from the discovery of gravitational time dilation, a phenomenon predicted by Einstein's theory. In the 1960s and 70s, experiments began to observe the passage of time at different altitudes, revealing that clocks closer to Earth's surface ticked more slowly than those high in the mountains. The closer an object is to a massive body, the greater the curvature of space-time, and thus the slower time passes. It was a revelation that took something as familiar as the ticking of a clock and turned it into a strange, elusive concept, dependent on one's position in the universe. These discoveries marked the beginning of a profound transformation in how we understood time. No longer was it a simple tick-tock, marching forward with unwavering consistency. Instead, time had become a malleable, complex phenomenon, stretching and bending in the presence of mass, energy, and motion. Each revelation deepened our connection to the cosmos, pulling back the veil on a universe that seemed to stretch and fold upon itself in ways we had never before imagined. And so, with the confirmation of these ideas, through the bending of starlight, the discovery of pulsars, and the revelation of time dilation, scientists began to uncover the hidden structure of time. The foundations of reality itself were being revealed to be far more complex, far more fluid than anyone had ever realized. And in the process, they unlocked the first key to understanding the great mystery of the universe. Time was no longer a simple, linear path. It was an entity unto itself, one that could bend, twist, and shape the fabric of the cosmos. As we continue to push the boundaries of our knowledge, we are left with the tantalizing question: if time is not absolute, if it can be shaped and manipulated by the very structure of the universe, what other secrets does it hold? What other mysteries lie waiting in the vast expanse of space beyond the reach of our understanding? The expansion of time. As the echoes of Einstein's revelations began to settle, the scientific community stood on the precipice of a new understanding. Time was no longer a static background to human life. It had become a living, breathing part of the universe. The journey from theory to discovery, however, was only beginning. A deeper exploration was now required, one that would expose the very threads that wove the fabric of space-time together. By the 1960s and 70s, the foundations of relativity had solidified, and the question shifted from "does space-time bend?" to "how does it bend?" It was during this period of intense curiosity that scientists began to probe deeper into the mechanisms of time dilation, aiming to understand how the warp of space-time influenced the very passage of moments. In 1971, a simple experiment in the sky began to reveal a truth that was both staggering and sublime. Time itself was not just relative on a cosmic scale, but also on Earth. Dr. J.C. Haffel and Dr. Richard Keating, two American physicists, set out to test Einstein's theory using atomic clocks. They flew cesium clocks aboard commercial airliners, carefully measuring the difference in time between the clocks aboard the planes and those at rest on the ground. The result was nothing short of extraordinary. The clocks on the planes ticked at different rates than those on the ground. Time moved slower for the clocks in motion as they neared the speed of travel. It was a moment of revelation. Time, the ticking heart of the universe, was not a constant even on Earth. The idea that time could be stretched or compressed based on velocity and gravity was no longer a mere theory. It was observable, measurable, and real. The experiment itself was relatively simple. Two clocks, one on an airplane, the other on the ground, but its implications were vast. As the airplanes soared above the Earth, they experienced less gravity, and as they sped through the atmosphere, they approached a fraction of the speed of light. In this altered state, the rules of time itself began to shift. The result of this experiment was clear. Time was elastic, a river whose flow was dictated by the terrain it traversed. But this wasn't just a curiosity. It was the door opening to a larger, more profound reality. As these revelations deepened, another question began to arise. Could time behave differently in other parts of the universe? Could time bend or stretch more dramatically in places of extreme gravitational pull, like near a black hole or the edge of a massive galaxy? And if time could warp in these ways, what would it mean for the universe itself? Could the very structure of space-time contain hidden pockets of time where moments were no longer consecutive, where time flowed differently, or perhaps ceased to flow altogether? This question was answered in a way that no one could have anticipated when, in 1967, Jocelyn Bell Burnell's discovery of pulsars shook the foundations of cosmic understanding. These dense, rapidly rotating stars, the remnants of supernovae, were more than just an oddity. They were cosmic clocks, pulsating with perfect precision. Every time a pulsar spun, it emitted an electromagnetic pulse at exactly the same rate, with a consistency so exact it could be used to measure time across the vast reaches of space. In their rhythmic pulse, pulsars became beacons for scientists. These ticking cosmic timepieces, unaffected by the warps of space-time around them, became key to understanding how time could exist within such a chaotic and dynamic universe. For years, pulsars were an enigma, their regular pulses thought to be the result of a simple mechanism. But as observations continued, it became clear that these stars were not just emitting light or radiation. They were providing the most accurate clocks ever known. By comparing the arrival times of pulsar signals from different points in space, astronomers were able to measure the warping of spacetime itself, confirming Einstein's predictions with unparalleled precision. Through these discoveries, a profound realization dawned. The nature of time was not something we could control or predict, but something that we had only just begun to understand. Time was not simply the ticking of a clock. It was part of the very structure of the universe, molded by the unseen forces that governed the cosmos. The pulsar, as it turned out, was a cosmic cornerstone, an instrument for measuring time not just here on Earth, but across the stars. They revealed the curvature of space and time in ways that were previously inconceivable, offering a new way of viewing the universe. Time, it seemed, could be bent and stretched, but it could also be measured with exquisite precision, allowing scientists to peer into the very heart of space itself. Yet, even as this new understanding of time began to take shape, it left behind questions that reached far beyond the reach of current scientific knowledge. What happens to time in the most extreme environments, in the presence of supermassive black holes, where the pull of gravity is so immense that it bends light and distorts the fabric of space-time? Could time freeze completely at the event horizon of a black hole, or could it even reverse, as some scientists speculated? And in those most extreme pockets of the universe, what of the future of time itself? Was the universe slowly bending toward a state where time itself might unravel, where moments might cease to exist? As the discoveries continued to unfold, the very idea of time began to change. No longer could it be seen as a steady, unchanging backdrop to human existence. Instead, time was revealed to be a cosmic player, influenced by the deepest forces of the universe. It stretched, it bent, it folded, but most profoundly it moved forward, carrying everything with it, regardless of how fast, how slow, or how warped it might seem. This journey, from Einstein's initial insights to the pulsar discoveries of the 1960s and the confirmation of time dilation through Haffel and Keating's experiment, marks only the beginning of our understanding of time's intricate role in the cosmos. Yet, for all that has been revealed, time remains a mystery, a force whose true nature still escapes our grasp. We may know its patterns, we may measure its passage, but the deeper questions, the ones that reach into the very heart of the universe, remain unanswered. What is time? What happens when we approach the edge of it? And if time itself is so malleable, could the universe we know be merely the beginning of something even greater? The journey of discovery is far from over, and as we continue to probe the mysteries of space-time, we come ever closer to understanding the very fabric of reality itself. Gravitational time dilation. As we continue our journey through the universe, time becomes more than just a measure of moments passing. It becomes a force in itself, bending and warping under the influence of the universe's grandest structures. The most profound of these distortions occurs in the presence of massive objects, where the very essence of time, that familiar ticking of the clock, begins to stretch and slow, altering our perception of reality itself. The phenomenon that allows us to understand this better is known as gravitational time dilation, and it is one of the most captivating aspects of Einstein's theory of relativity. For the first time, scientists were faced with the realization that time could move differently, depending on the strength of gravity at a given location in space. The presence of mass, the very fabric of matter, could influence the passage of time itself. Gravitational time dilation was first confirmed on Earth in the 1970s, through a series of experiments that measured the behavior of atomic clocks placed at different altitudes. Clocks placed at higher elevations, where gravity was weaker, ticked slightly faster than those on the ground, where gravity was stronger. This was not a subtle effect. The discrepancy was measurable, and with modern atomic clocks, the difference could be precisely quantified. But the true implications of gravitational time dilation stretch far beyond our planet. As mass increases, as objects grow larger and denser, their influence on spacetime becomes more pronounced. It is in these extreme environments that the most dramatic effects on time are seen. Perhaps the most stunning example of gravitational time dilation can be found near black holes, those mysterious, all-consuming objects in space where gravity reaches such extreme levels that even light cannot escape. The boundary around a black hole is known as the event horizon. Once something crosses this threshold, it is forever drawn in, lost to the singularity at the center. But before crossing this boundary, something extraordinary happens to time itself. Imagine standing at the edge of a black hole, watching an object fall toward its event horizon. As it nears the boundary, the object's movements appear to slow. Time, for the object, is not moving at the same rate as for you. Its progress through time seems to halt, suspended in a strange, stretching moment. To an outside observer, this object would appear to freeze in time as it crossed the event horizon, never actually disappearing from sight, but remaining perpetually frozen at the edge. This idea is not a theoretical construct alone. It is based on the calculations of Einstein's general relativity, confirmed by numerous observations. For instance, as matter spirals into a black hole, the behavior of time becomes increasingly distorted. To the distant observer, the object appears to slow down progressively, its light stretching and fading, its passage through time slowed to a crawl. For the object falling into the black hole, however, time behaves differently. From its perspective, it crosses the event horizon without any sensation of time dilation. This is the beauty and the horror of gravitational time dilation. Time is not the same for everyone, everywhere. It is influenced by the fabric of space itself, shaped by mass, energy, and gravity in ways that the human mind struggles to comprehend. This concept is no longer purely academic. In recent years, the event horizon of black holes has been photographed by the Event Horizon Telescope collaboration. In 2019, the world watched as the EHT unveiled the first-ever image of a black hole's shadow, the glowing disk of matter swirling around it. This observation brought us face-to-face with the curvature of space-time in its most extreme form. Time itself was being stretched around this massive object, frozen at its very core. But black holes are not the only places where gravitational time dilation can be witnessed. The effects of this phenomenon are also visible on a more familiar scale, though they are more subtle. Consider the Earth and its gravitational field. The further an object is from the Earth's surface, the less it feels the pull of gravity, and the more quickly time can pass for it. In fact, the very essence of our GPS satellites, those indispensable tools we use to navigate our world, depends on our understanding of gravitational time dilation. Satellites orbiting the Earth move at speeds that make time pass more slowly for them compared to clocks on the surface. Additionally, they experience weaker gravitational forces, so time ticks slightly faster for them as well. Engineers at NASA, when designing these satellites, had to account for these time differences. Otherwise, the positioning data provided by the satellites would gradually drift, becoming useless over time. Thus, the seemingly mundane act of getting directions from a GPS system is a profound application of the theory of relativity. Time, as it turns out, is not just something we feel passively. It is a force, and in certain situations, its behavior can alter the way we navigate our world. On the grandest scale, however, the most stunning instances of time dilation are found in the most extreme environments, around massive galaxies, black holes, and supernovae. The discovery of time dilation in these regions opens up new vistas of the universe, suggesting that the very structure of time is shaped by the forces that govern the cosmos. In places of immense gravity, time itself stretches out, allowing for an entirely new way of experiencing the universe. But what does this all mean? If time can slow down and speed up depending on where you are, how do we understand the passage of time across the universe? If someone were to stand on the surface of a neutron star or near the event horizon of a black hole, what would time mean to them? Would their experience of life be the same as ours, or would they be living in a different temporal dimension altogether? And if we could measure this warping of time across the galaxy, could we one day unlock the mysteries of how time itself originated? The answers to these questions lie in the ongoing exploration of the universe, as scientists continue to test the boundaries of relativity and gravitational time dilation. New space missions, new telescopes, and new technologies are allowing us to peer deeper into the cosmos, to measure time with ever greater precision, and to push the boundaries of human understanding. Yet, as we learn more, we are left with a sense of awe and humility. The nature of time remains elusive, stretching out before us like an infinite river whose course we can only glimpse, never fully grasp. And, as we continue to look deeper into the void, we may come to realize that the most profound truths about time, about how it bends, how it warps, how it defines the very structure of the universe, are still waiting to be uncovered. Time, as we know it, is not merely the ticking of a clock. It is an entity unto itself, a force that shapes the cosmos and perhaps, just perhaps, holds the key to understanding the fate of the universe itself. The void beyond time. As we venture further into the heart of the cosmos, we encounter a strange and unsettling presence: the void. This isn't simply the absence of light or the emptiness between stars. It is something deeper, more profound, a vast stretch of nothingness so immense that it dwarfs the limits of our understanding. It is a place where the very fabric of space-time appears to unravel, where the laws that govern the universe seem to fade into the unknown. It is the Great Void. In the early 20th century, when Einstein's theory of relativity first began to reshape our understanding of space and time, few could have predicted the discovery of such an anomaly. A region of space so vast, so empty, that it defies all conventional logic. How could this vast emptiness exist in a universe that, at every turn, is teeming with matter? Where did all the stars, galaxies, and cosmic structures go? And if the universe is expanding, why does this expanse of nothingness seem to grow as well? The Great Void was first detected in the 1980s, as astronomers, armed with more powerful telescopes and advanced methods of mapping, began to explore the distant reaches of space. It was a seemingly impossible discovery, a massive region of space where the usual galactic structures simply didn't exist. No stars, no galaxies, just an infinite stretch of emptiness. It was not just a gap in the universe, but something more profound, an entire region that seemed to defy the very notion of space. This discovery would set in motion a series of revelations that would reshape our understanding of the cosmos. Scientists initially hesitated to believe what they were seeing. How could such an emptiness exist? How could a space so vast, stretching across hundreds of millions of light years, remain void of the matter that fills the rest of the universe? They combed through the data, analyzing each observation, searching for an explanation, but what they found only deepened the mystery. The Great Void was not just a single anomaly, it was a part of a much larger pattern. The universe was not uniformly filled with galaxies and stars, as had long been assumed. Instead, there were regions, vast stretches of space, where galaxies were conspicuously absent. The universe was an intricate web of interconnected structures, with dense clusters of galaxies separated by vast voids. Vast, interconnected spaces that seemed to make up the very skeleton of the cosmos. These voids, stretching across hundreds of millions of light years, were not mere gaps in the universe. They were part of a larger cosmic structure, a complex network of filaments and voids that gave shape to the universe itself. The discovery of the Great Void was a turning point, revealing that the universe's structure was far more intricate than anyone had imagined. The very idea of a void, of something being completely empty, seems to violate every intuition we have about the cosmos. After all, the universe is teeming with matter, from the smallest particles to the largest galaxies. The concept of nothingness is, in many ways, a paradox, and yet the Great Void exists. It is real, and its scale is staggering. How could something so massive, so profound, be so empty? But the void is not just empty space. It is, in a sense, an area where the very laws of the universe seem to break down. In the absence of galaxies, stars, and other forms of visible matter, these regions challenge our understanding of space and time. What does it mean to have nothingness on such a vast scale? How does it affect the flow of time itself? The Great Void, as it turns out, may not be entirely empty. It is a place where the influence of gravity appears to be reduced. In the void, the usual rules of cosmic interaction seem to break down. Stars and galaxies, which are bound by the gravitational forces of the universe, seem to be absent in these regions. In the absence of matter, gravity weakens, and the fabric of spacetime becomes stretched. Time itself may pass differently here, slower than it does in more dense regions, as the lack of mass disrupts the curvature of spacetime. The discovery of the Great Void also posed a challenge to our understanding of cosmic evolution. If the universe is expanding, as we now know it is, then these voids should also be growing. But why do they exist at all? What could cause such a profound emptiness in the fabric of the universe? And could this emptiness hold the key to understanding the very nature of space, time, and gravity? As astronomers continue to map the universe, they have found that the voids are not simply passive regions of empty space. They are active, dynamic structures, stretching and expanding as the universe itself grows. The Great Void is not a frozen moment in time, but a constantly shifting, evolving feature of the cosmos. It is a place where matter is drawn away, leaving a deep and empty space in its wake. And, as the universe continues to expand, these voids are growing, stretching outward, reshaping the cosmic landscape. The existence of these vast empty spaces forces us to confront some of the deepest questions about the nature of the universe itself. What are these voids telling us about the forces that shape the cosmos? How do they fit into the grand puzzle of cosmic evolution? And if time itself is malleable, as Einstein proposed, how does it behave in these vast, empty expanses? Could these voids be a window into something far beyond our understanding, a deeper layer of reality that remains hidden from view? In the search for answers, scientists have proposed a number of theories. Some suggest that the voids are a natural consequence of the universe's expansion, the result of the cooling and spreading of matter over billions of years. Others believe that they may be the result of dark energy, the mysterious force that is accelerating the expansion of the universe. Could dark energy be responsible for creating these vast, empty spaces, pushing galaxies apart and leaving behind stretches of nothingness? Still others have proposed that the voids could be the remnants of an even more profound phenomenon, the collapse of matter into black holes, or perhaps even the existence of other universes. Could the great void be a window into a parallel universe, an alternate reality where the rules of space and time are different from our own? Could it be a relic of the Big Bang itself, a shadow of the universe's earliest moments? Theories abound, but the answers remain elusive. What we do know is that the great void is a place of mystery, a cosmic enigma that beckons us to look deeper into the heart of space and time. And as we continue to explore the universe, we may one day find that the key to understanding the cosmos itself lies hidden within these vast, empty stretches of space. Theories and speculations. As scientists continue to probe the vast unknowns of the great void, they begin to unravel more than just empty space. The discovery of such vast, seemingly abandoned regions of the universe compels us to rethink the very fabric of reality. What could explain the existence of such immense, hollow expanses? How do these voids fit into the grand narrative of cosmic evolution? And what forces are at work shaping these empty spaces? As with many of the greatest mysteries of the cosmos, the answers are not easily found, but rather scattered across a landscape of scientific speculation, complex theories, and intellectual curiosity. One of the most intriguing and often discussed theories concerning the origin of the Great Void and other such emptinesses involves dark energy, the mysterious, invisible force that seems to be driving the accelerated expansion of the universe. While the precise nature of dark energy remains one of the most profound puzzles of modern physics, its existence was inferred through observations of distant supernovae in the late 1990s. These observations revealed that the expansion of the universe was not slowing down, as had been expected, but rather speeding up. Something unseen and powerful, some force or energy, was pushing galaxies apart. But what could this force be? Dark energy is thought to make up around 70% of the total energy content of the universe, but it has yet to be directly detected or understood. It is theorized that dark energy could be responsible for the observed voids in the universe. If it causes the accelerated expansion, then it could also be pulling galaxies apart, leaving large regions of space devoid of matter. These vast cosmic voids could, in a sense, be the result of dark energy pushing matter outwards, creating pockets of emptiness as the universe expands. But how exactly this would occur, and what dark energy actually is, remains speculative. Some physicists suggest that dark energy is a form of vacuum energy, a force arising from the quantum fluctuations of empty space itself. According to quantum theory, even a vacuum, traditionally thought of as empty space, is not truly empty. Instead, it is filled with temporary particles that appear and disappear at an almost infinitesimal timescale, a phenomenon known as quantum fluctuations. In this view, dark energy could be the result of a false vacuum, a state in which the quantum vacuum is in a higher energy state than it should be. causing it to exert an outward pressure that drives the expansion of the universe. This idea, if true, raises fascinating possibilities. Could the Great Void be a remnant of such a quantum fluctuation? Could it be that the voids we observe today are the result of an unstable phase in the universe's early history, where quantum fluctuations gave birth to massive, empty regions of space? The concept of a false vacuum also carries ominous implications. If the universe were to transition into a lower energy state, a true vacuum, what would happen to the fabric of spacetime? Would the laws of physics as we know them break down? Would the universe itself cease to exist, or would it undergo a dramatic transformation? These are questions that, for now, lie in the realm of speculative cosmology. Another theory suggests that the voids may be a consequence of cosmic inflation, the rapid expansion of the universe in its earliest moments, just after the Big Bang. During inflation, the universe expanded exponentially in a fraction of a second, driven by an enormous burst of energy. This incredibly rapid expansion could have caused certain regions of space to stretch beyond the reach of matter, creating vast, empty spaces, voids, where galaxies could not form. If this theory holds, the Great Void and other similar structures in the universe might be a natural outcome of the very expansion that gave birth to the universe itself. These voids could be the remnants of regions that, due to the rapid stretching of space-time, were never filled with matter. However, the most intriguing speculation surrounding the Great Void revolves around the concept of parallel universes, a theory that proposes that our universe might be just one of many in a larger multiverse. In this view, the Great Void could be the boundary between our universe and another, a region where the laws of physics differ and where the matter and energy from another universe are inaccessible. The voids, then, might represent the empty spaces between these universes, where nothing can exist because the laws governing space, time, and matter are different from those in our own universe. The idea of the multiverse is far from new. It has emerged in various forms throughout the history of physics, from the concept of parallel worlds in quantum mechanics to the idea of multiple universes in string theory. If the Great Void were, in fact, a gateway between universes, it would challenge everything we know about reality. It would imply that our universe is not unique, but rather part of a much larger cosmic landscape, where other universes with their own distinct physical laws and properties could exist. These universes might not even be detectable, except for the faint traces of their presence at the edges of the Great Void. This idea pushes the boundaries of science and philosophy, asking us to reconsider the very nature of reality. What does it mean for us to exist in this universe if there are others beyond our reach? If our universe is just one of many, what is the purpose of existence? These questions, though tantalizing, remain far beyond our current scientific capabilities. And yet, they offer a glimpse into a future where the boundaries of space, time, and reality itself could be explored in ways that we can only begin to imagine. As we attempt to understand the Great Void and the forces that shape it, we are confronted with a universe far more complex than we could have anticipated. The voids, dark energy, quantum fluctuations, and parallel universes are all pieces of a much larger puzzle, one that humanity is only beginning to solve. Yet, even as we stretch our understanding of the cosmos, we are reminded of how much we still do not know. Each discovery, each new theory, brings us closer to understanding the nature of the universe, but also deeper into its mysteries. The void is a place where our knowledge ends and speculation begins, a reminder that there is still so much to uncover in the vast expanse of space. Scientific tools and ongoing testing. As the mystery of the great void deepens, the universe itself seems to challenge us at every turn, demanding that we expand the very tools we use to measure, observe, and understand it. To confront the vast emptiness of space, to peer into regions where no stars or galaxies reside, scientists must push the boundaries of technology, relying on increasingly sophisticated instruments. The void is not something we can touch or feel. It is an invisible presence, detectable only through the subtle traces it leaves in the cosmos. To understand the void, we must develop the tools capable of unraveling its secrets. One of the most powerful tools in modern astronomy is the telescope, a device that has, for centuries, allowed us to reach out into the vastness of the universe. From the early days of Galileo's crude lens to the cutting-edge telescopes of today, we have continually improved our ability to look deeper into the cosmos. Yet, as astronomers began to map the voids, it became clear that traditional optical telescopes would not suffice. The Great Void, and others like it, were not visible in the traditional sense. They contained no stars to observe, no bright nebulae to capture. Instead, they were detected through the absence of light, the absence of matter. To study these dark expanses, scientists turned to the more subtle methods of observation, relying on radio telescopes and infrared observations. These instruments can detect emissions that are invisible to the naked eye, such as the faint radio signals emitted by galaxies, or the infrared radiation coming from distant objects. By scanning vast regions of the sky, these telescopes allow us to map the structure of the universe, not just by looking at what is there, but by studying what is not there. The Sloan Digital Sky Survey, SDSS, one of the most ambitious sky surveys ever undertaken, has been instrumental in uncovering the structure of the Great Void. By observing millions of galaxies across the sky, astronomers were able to create a detailed map of the universe, revealing large, empty regions of space that had previously been unnoticed. The SDSS has allowed scientists to chart the location and size of cosmic voids with unprecedented precision, mapping the gaps between galaxies and helping to determine their role in the broader structure of the cosmos. Another groundbreaking instrument is the Hubble Space Telescope, which has provided some of the clearest and most detailed images of the distant universe. Hubble's observations have allowed scientists to study not only the stars and galaxies within the voids, but also the very structure of spacetime itself. By observing distant galaxies and measuring their redshifts, astronomers have been able to confirm the existence of these voids and measure their rate of expansion. These measurements have provided valuable data about the nature of the voids and the role they play in the expansion of the universe. Yet, for all the technological advances we have made, the study of the void remains an imperfect science. While we have mapped the locations of the largest voids in the universe, our understanding of how they form and what drives their expansion remains limited. The voids, after all, are not simply empty regions. They are dynamic, ever-changing features of the universe. As the universe expands, these voids are stretching and growing, leaving gaps in the cosmic web. To fully understand them, we need to observe them in real time, watching as they evolve, and perhaps even as they affect the surrounding galaxies and matter. In this pursuit, gravitational wave detectors such as the LIGO, Laser Interferometer, Gravitational Wave Observatory, and Virgo have become invaluable. These instruments are designed to detect the faint ripples in spacetime caused by massive events like the collision of black holes or neutron stars. While these detectors are not directly aimed at studying voids, they are revealing deeper layers of spacetime that could provide important insights into the nature of these empty regions. By measuring the effects of gravitational waves traveling through the voids, scientists can learn more about the structure and evolution of the voids themselves. Beyond the physical instruments, the study of the Great Void is also taking place through computer simulations and theoretical modeling. By using supercomputers to simulate the behavior of galaxies, dark matter, and dark energy, scientists can explore how these cosmic voids might have formed and how they continue to evolve. These simulations allow researchers to model the expansion of the universe over billions of years, helping to identify the forces that shape the cosmic web and to predict the future evolution of the voids. One of the most significant breakthroughs in understanding the voids came with the use of cosmic microwave background (CMB) radiation. The CMB is the afterglow of the Big Bang, the faint radiation that fills the universe and serves as a snapshot of the universe's infancy. By studying the CMB, scientists can learn about the earliest moments of the universe and how the matter that would later form galaxies and stars was distributed. The study of the CMB has provided important clues about the formation of cosmic voids, suggesting that the voids may have formed early in the universe's history, as areas of lower density where matter was less likely to collapse and form galaxies. In the coming years, new missions such as the James Webb Space Telescope, JWST, will push the boundaries of our understanding even further. The James Webb Space Telescope, set to launch in the near future, promises to give us an unprecedented view of the distant universe. Its infrared capabilities will allow it to peer through the dust and gas of galaxies, and to study the first stars and galaxies that formed after the Big Bang. With its help, we may finally be able to understand how cosmic voids came to be, and what role they play in the evolution of the universe. But despite these remarkable advancements, the voids remain enigmatic. As technology improves, we are getting closer to understanding how these vast regions of emptiness fit into the grand structure of the universe. But even as we gain more insight into the void's nature and behavior, we are reminded of the limitations of our current knowledge. The universe, vast and incomprehensible, continues to surprise us at every turn. And in the case of the Great Void, the question remains, is it truly empty? Or is there something hidden in its depths, a secret yet to be uncovered? The Great Void stands as a reminder of how much we still have to learn. In the quiet expanse of space, time itself bends and warps, and gravity behaves in ways we can scarcely comprehend. And yet, despite the unknowns, the scientific community continues to press forward, developing new tools, refining old theories, and pushing the boundaries of human knowledge. As the universe unfolds before us, one thing is certain. The Great Void is not an anomaly to be ignored, but a clue to a deeper mystery, one that lies at the heart of everything we know about space, time, and the universe itself. Philosophical reflection: the nature of nothingness. As we look into the vast emptiness of the Great Void, we find ourselves standing on the precipice of something that challenges not only our understanding of the universe, but also our very understanding of existence itself. The Great Void, that vast expanse of space where galaxies and stars seemingly vanish, forces us to confront an unsettling truth. Is there truly such a thing as nothing? In our attempts to define the universe, to map its stars and galaxies, have we overlooked the presence of emptiness? Or is it that this emptiness itself has always been the most profound force in the cosmos? For centuries, humanity has struggled with the concept of nothingness. Philosophers have pondered whether true emptiness can even exist, or whether what we perceive as nothing is simply the absence of something we have yet to understand. In ancient times, the void was seen as a paradox, something that could neither exist nor not exist. It was a place where the laws of nature seemed to break down, and questions about life and the universe became intertwined with the mystery of existence itself. Yet, as we peer deeper into the great void, we must ask, what if this emptiness is not the absence of something, but rather a manifestation of forces and phenomena that we are still not equipped to comprehend? Perhaps it is not true emptiness at all, but a vast region where our understanding of space, time, and energy reaches its limits. The great void presents us with a strange contradiction, an absence so profound that it seems to defy all our assumptions. And yet, it is in this very absence that we find an even deeper mystery. What does it mean for something to be absent? What does it mean for space to be empty? For all our study of galaxies, stars, and black holes, how often have we overlooked the significance of the void itself? The emptiness of space is not merely a vacuum, as we once believed. It is a region where the usual forces of gravity and light seem to lose their grip. A place where time itself behaves differently, perhaps stretching and distorting in ways that elude our understanding. But it is also a place that forces us to reconsider the very idea of reality. In some ways, the great void seems to question the very nature of existence. If this vast region is truly empty, what does it mean for our understanding of the universe? Can the concept of emptiness itself be considered a force, something that shapes the very structure of the cosmos, perhaps even guiding the evolution of galaxies and the movement of stars? What does it mean for us to be part of a universe that contains such vast, seemingly infinite stretches of nothingness? Are we, too, merely a fleeting speck in a universe whose true nature is far more complex and incomprehensible than we could ever imagine? The void, in this sense, forces us to confront something more than just a physical phenomenon. It challenges our deepest, most existential questions. What is the nature of existence itself? If space can be both filled and empty, if time can stretch and bend, what is the fundamental structure of the universe? And, perhaps most unsettling of all, what does it mean for our own place in this vast, ever-expanding cosmos? If the universe itself is expanding, with voids growing larger as galaxies are pushed farther apart by the force of dark energy, then where does that leave us? What happens to time in these regions where the very concept of space begins to fall apart? If the great void continues to expand, what does that mean for the future of the universe? Could the universe one day reach a point where even the most fundamental forces cease to work as we understand them? Philosophically, the great void beckons us to reconsider the very idea of progress and motion. In a universe that is constantly expanding, constantly evolving, the existence of a region of nothingness challenges our assumptions about what is real. We have long assumed that the universe is a place where matter and energy will always be present in some form, that the stars will continue to burn and the galaxies will continue to spin in an eternal dance. But the great void forces us to confront a future where this cosmic dance may slow, where the energy and matter that fuel our universe may eventually dissipate into emptiness. It is a future in which the very fabric of spacetime may begin to stretch out beyond our reach, leaving behind only the echo of a once thriving cosmos. The void, then, is not merely the absence of stars or galaxies. It is a reflection of our own cosmic fate. It is a place where the very laws of the universe seem to bend and break, where our understanding of space, time, and gravity is stretched beyond its limits. As we continue to explore the mysteries of the void, we are forced to reconsider the meaning of existence itself. Are we living in a universe that is destined to collapse into emptiness, where all matter and energy will eventually vanish into nothingness? Or is the void simply a temporary state, a passage between different stages of cosmic evolution, waiting for new forms of life, new galaxies, new forces to emerge from its depths? The more we learn about the void, the more we realize that it is not just a scientific anomaly. It is a cosmic mirror reflecting our own place in the universe. The void, in its infinite emptiness, is a reminder that we, too, are part of something much larger than ourselves. We are bound to the same forces that shape the universe, drawn together by gravity, propelled by the same mysteries that govern the stars and galaxies. And yet, at the same time, the void forces us to confront the limits of our understanding, reminding us that no matter how much we learn, there will always be mysteries beyond our grasp. As we stand at the edge of the great void, gazing into the depths of space, we are left with more questions than answers. But perhaps, in the end, that is the true gift of the void. It is a reminder that there is still so much left to discover, so much left to learn. It challenges us to look deeper into the cosmos and to reconsider what we know about the universe. And, in doing so, it pushes us to seek the answers to the most fundamental questions of existence. And so, the great void stands as a testament to the mysteries that lie just beyond our reach. It is a place where the known and the unknown intersect, a cosmic riddle that we may never fully solve, but one that will continue to inspire, provoke, and challenge humanity for as long as we look to the stars. The fate of the universe. As we stand at the precipice of understanding, gazing into the infinite expanse of the great void, one question lingers above all others. What is the ultimate fate of the universe? The void, vast and incomprehensible, holds the key to a mystery that has captivated minds for centuries. What happens when the universe continues to expand, when the galaxies drift further apart, and when the light that once connected them begins to fade? The discovery of cosmic voids has only deepened our awareness of the universe's impending transformation. And though we may not yet fully comprehend the forces at play, the journey to understanding the fate of the cosmos has begun. In the early 20th century, when the theory of relativity first revolutionized our understanding of space and time, the idea of an expanding universe was still a distant and speculative notion. But as the decades passed, observations began to confirm what had once been inconceivable. The universe was not static, but was, in fact, expanding. The realization came through the work of Edwin Hubble, who, in 1929, discovered that galaxies were receding from us in all directions. The farther a galaxy was from Earth, the faster it appeared to be moving away. This was a revelation of profound significance. If galaxies were moving apart, it could only mean one thing. The universe itself was expanding. At the time, the idea of an expanding universe seemed both exhilarating and unsettling. If the universe was expanding, then it must have started from a single point, a beginning, a singularity, an infinitesimal speck from which all of existence burst forth. This revelation would become the foundation for the Big Bang Theory, the prevailing cosmological model that describes the universe's origin as an explosion of space, time, and energy. But even as this theory offered an explanation for the universe's birth, it also raised new questions. If the universe is expanding, where is it expanding to? What lies beyond the confines of the cosmos, and what will happen when this expansion reaches its limit? These questions became even more urgent with the discovery of dark energy, a mysterious force driving the accelerated expansion of the universe. It is now understood that dark energy makes up roughly 70% of the total energy content of the universe. Yet, despite its overwhelming influence, dark energy remains a shadowy enigma, a force that scientists can observe only through its effects on the cosmos. As dark energy continues to push galaxies further apart, the expansion of the universe is not slowing down as once expected. Instead, it is speeding up, driving galaxies into the farthest corners of the universe, further away from one another. The Great Void, these immense expanses of empty space, grow larger with each passing day, and it appears as though the universe is entering a phase of inevitable isolation. The concept of a cosmic horizon emerges in this context. This is the point beyond which light and matter can no longer travel to reach us, because the universe is expanding too rapidly. As the voids grow and galaxies recede, the distance between us and the farthest reaches of the universe increases, and eventually, we will no longer be able to observe the light from the distant stars that once illuminated the night sky. This is not the distant future. It is an inevitable outcome of the forces at work within the universe. In billions of years, the night sky will grow darker, as the galaxies we know and love will drift beyond the cosmic horizon, leaving us to gaze into an empty void. This scenario is only one possible future. The most widely accepted theory of the ultimate fate of the universe is known as the Big Freeze. In this scenario, the continued expansion of the universe, driven by dark energy, leads to a gradual cooling of the cosmos. As galaxies drift farther apart, they will lose the gravitational pull that binds them together, causing the stars to burn out one by one. Over trillions of years, stars will exhaust their fuel, leaving behind cold, dark remnants. The gas and dust that once formed the building blocks of stars will be scattered, and over time, even the remnants of dead stars will be stretched and dispersed by the expansion of spacetime itself. Eventually, the universe will become a vast, cold, lifeless expanse. Dark voids stretching out across a cosmos that no longer holds the promise of creation. Yet, this scenario does not end the story of the universe. While the Big Freeze describes the ultimate fate of the universe in its current form, there are other theories that explore what might happen after the universe's expansion reaches its limits. One such theory is known as the Big Rip, a scenario in which the expansion of the universe accelerates to such an extreme degree that the very fabric of space-time begins to tear apart. In the Big Rip, the force of dark energy increases exponentially, pulling apart galaxies, stars, planets, and even atoms. The universe would be torn asunder, and all matter would be destroyed in a final, catastrophic end. It is a horrifying thought, but not an entirely implausible one. In this scenario, the Great Void would not only grow, it would become an all-encompassing force that consumes everything, unraveling the very structure of reality itself. Time, space, and matter would cease to exist as we know them, leaving behind a universe bereft of everything we understand. The void, in its purest and most terrifying form, would become the ultimate expression of nothingness, as the very laws of physics would be undone. There is, however, another possibility: the Big Bounce. According to this theory, the universe's current expansion could eventually reverse, causing everything to collapse back into a singularity, much like the Big Bang itself. In this model, the universe oscillates through cycles of expansion and contraction, with each cycle culminating in a bounce that leads to a new Big Bang, and the process begins again. In this scenario, the Great Void would not be a permanent feature of the universe, but rather a temporary state before the universe undergoes a rebirth. The Great Void would be a pause, a stillness before the next cycle of cosmic creation. At the heart of these competing theories lies a simple truth: the future of the universe is uncertain. The forces at work in the cosmos, dark energy, gravity, and the curvature of spacetime, are still poorly understood, and new discoveries are continually shifting our understanding of how the universe will evolve. What is certain, however, is that the universe is far from static. It is a living, breathing entity, constantly shifting and changing. Whether it ends in cold emptiness, total destruction, or infinite rebirth, the universe will continue to evolve, pushing the boundaries of time and space in ways we cannot yet fully comprehend. As we gaze into the Great Void, we are reminded that the universe itself is a vast, mysterious process, one that continues to unfold despite our best efforts to understand it. The void, in all its emptiness, is not the end of the story. It is a chapter, a stage in the ongoing evolution of the cosmos. And though the ultimate fate of the universe may lie beyond our reach, the journey to understand it is what gives our lives meaning, propelling us forward into the unknown with curiosity, wonder, and the eternal quest for knowledge. The infinite horizon. As the universe unfolds before us in all its vastness, the concept of an infinite horizon becomes not just a metaphor, but a scientific reality, an invisible boundary beyond which we can never reach. This horizon is not made of matter, nor can it be touched by the hand of human curiosity. It is a product of the universe's accelerating expansion, a cosmic edge beyond which all that we can see, measure, and understand will inevitably fade into darkness. The Great Void, stretching ever outward, represents this boundary, this limit to human perception. It is a horizon we cannot cross, a place where the laws of physics become increasingly uncertain, and where the very nature of time and space begins to blur. The discovery of this cosmic horizon was made possible by the realization that the universe is not just expanding. It is expanding faster than the speed of light in certain regions. This acceleration, driven by the mysterious force known as dark energy, is causing galaxies to recede from one another at an ever-increasing rate. The further away a galaxy is from us, the faster it appears to be moving. In fact, galaxies that are far enough away are receding at such a speed that their light will never reach us, no matter how much time passes. These distant galaxies have crossed a threshold, beyond which their light can never again travel to our world. They have crossed the cosmic event horizon, a boundary beyond which the universe itself is lost to us. The significance of this event horizon is profound. It represents the ultimate limit of human knowledge. While we can study the galaxies within our observable universe, the regions beyond this horizon are forever out of reach. The universe, it seems, is slowly pulling away from us, and there is nothing we can do to stop it. We can see only the tiniest fraction of the cosmos, and as time goes on, our view of the universe will only become smaller. The Great Void, a dark expanse that seems to stretch endlessly before us, will only grow. swallowing the galaxies that we once saw as part of our cosmic neighborhood. This expansion, driven by dark energy, brings to the fore the deep philosophical questions about the nature of existence. If the universe is expanding, if time is stretching, then what does this mean for the future of space itself? Are we alone, isolated by the ever-increasing distance between us and the rest of the cosmos? Will our understanding of the universe continue to shrink until there is nothing left to observe? As the light from the farthest galaxies fades, we are left to wonder, does the universe have an end? And if so, what does it look like? One of the most unsettling implications of the cosmic event horizon is the realization that the future of the universe is, in many ways, already determined. The accelerating expansion of the universe means that, over time, galaxies will be drawn further apart, and the observable universe will continue to shrink. Eventually, we will lose sight of all but the closest galaxies, and the night sky will darken. The stars we see today will fade away, their light stretched beyond recognition. The great void will expand to the point where it consumes the entire, observable universe, leaving behind a universe of cold, isolated galaxies. The future of life in such a universe seems bleak. Without the gravitational pull of other galaxies, stars will burn out, and the energy that sustains life will dissipate. As stars die, they leave behind black holes, which will eventually evaporate through a process known as Hawking radiation, named after the famous physicist Stephen Hawking. This radiation, emitted by black holes, will cause them to lose mass over time, slowly vanishing into the void. The heat death of the universe, the eventual fate of all things, is a terrifying possibility. A universe in which all matter has decayed, all energy has dissipated, and nothing remains but a dark, cold void. Yet, even in this bleak future, there is something strangely humbling about the cosmic horizon. It reminds us that the universe is much larger, much more complex than we could ever truly grasp. The vastness of the void, the expanse beyond the event horizon, forces us to confront our place in the cosmos. In the face of such incomprehensible distances, we are reminded of how small we are, how fleeting our existence is in the grand scheme of things. We are but a brief moment in the eternal unfolding of the universe, a tiny speck on the edge of an ever-expanding cosmos. The great void, stretching out before us, is a reminder that there is so much more to the universe than we can possibly comprehend. But even as the cosmic horizon recedes, there is still a deep sense of wonder in the pursuit of knowledge. Despite the unknowable vastness of the universe, the human spirit continues to search, to explore, to reach out into the unknown. We may never fully understand the universe's end, nor will we ever cross the event horizon to witness the great void in its entirety. But in our search for answers, we come closer to understanding the very essence of reality itself. The questions we ask, the discoveries we make, shape our understanding of existence, and in doing so, give meaning to our place in the cosmos. As we continue to explore the mysteries of the universe, we are reminded that our understanding of time, space, and the cosmos is far from complete. The great void, the event horizon, and the accelerating expansion of the universe are not the final chapter in the story of the cosmos. They are merely the beginning. Each discovery, each observation, pushes us closer to the truth. And though we may never cross the cosmic horizon, our journey of discovery will continue, unfolding like the fabric of spacetime itself, ever expanding and ever deepening. As we stand at the edge of the great void, peering into the abyss where light and matter fade into an infinite stretch of emptiness, we are left with more questions than answers. The void is not merely the absence of stars and galaxies, but a profound mystery that continues to elude our understanding. It is a cosmic riddle, a place where the very laws of space and time stretch and bend, forcing us to rethink everything we know about the universe. In our quest to understand the void, we have uncovered some of the deepest secrets of the cosmos: dark energy, the expansion of the universe, and the strange, mysterious forces that shape the fabric of reality itself. Yet, even as we learn more, we are reminded of the limits of human knowledge. The great void, with all its silence and isolation, is a humbling reminder that there is still so much we do not understand. The universe, in all its complexity, continues to unfold before us, and the void remains one of its most profound and enigmatic features. As we push the boundaries of science, exploring the vast emptiness between the stars, we find ourselves drawn back to the same timeless questions. What is the true nature of existence? What lies beyond the horizon of the observable universe? And, perhaps most haunting of all, what does the great void reveal about the ultimate fate of the cosmos? The answers may never fully be within our grasp, but the search itself drives us forward, deeper into the mysteries of the universe. The great void remains, a silent witness to the vast, unfathomable expanse that stretches beyond our understanding. And in the quest to understand it, we take one step closer to understanding the very nature of the universe, time, and our place within it.